right, so let's keep going here. We're gonna do a little bit of an extra. Happened. I guess that's perfectly acceptable to have a little bit of deviation. So if you didn't do as well as you thought you did or had hoped, but that's okay. Remember, this course is about learning. I want you to pick up something out of this. I don't expect you to have mastered the material. You're okay. Just keep doing what you're doing. Keep doing the homeworks. Try your best on the test. You'll be okay. The only way that you're really going to fail my class is if you just refuse to do anything. You do nothing. If you don't even try, you don't turn things in, then you're probably going to get the grade turned. But if you're genuinely trying, you're going to be okay. So let's first do kind of a fun little energy problem. Just to kind of just warmed up before we go into anything else. I've posted the notes for the next chapter. I want to see how far I get today before I assign the next homework, but you can expect the next homework to be due sometime next week, late next week, but I'll let you know when I post it. A note on homework, by the way, it is your responsibility to look at WebAssign periodically and know when homework assignments are due. Some of you have been waiting until the last minute and the day the assignment's due to even bother to look at it. And as a result, some of you have been bitten in the ass by that. So my suggestion is keep track of your homework. Keep track of what's due. Generally, you should expect a homework assignment every week. Don't make assumptions that just because there's a test coming up that you may not have a homework assignment. But you need to look. It is your responsibility. This is big boy college, so this is how this works. All right, having said that, let's do something a little more fun. So I'm sure over spring break, you guys all did nothing but think about physics. And I know you didn't, that's okay, because neither did I. So I want to start with something kind of fun. So I mentioned to you a few weeks ago that I was going to show you an energy problem where we can use our knowledge of kinetic potential energy to determine how hard you need to slap a frozen chicken to cook completely. It seems silly and nonsensical, and it is. But the point here is not to validate the feasibility of this, but I want you to see the physics behind it. Because really it's what we do as physicists, is somebody will come up with a problem, somebody will come up with a question and ask us, is this possible? And you need to have enough knowledge of physics to know where to begin. How do I begin to show this is possible or not? So the chicken slapping problem is, let's assume that, now you guys know I can't draw, so let's pretend that whatever this is about to look like is a frozen rotisserie chicken. I guess that looks reasonable. Generally no head, but fine. So walk. You don't like to think. All right. So Art, can you hear me?
Okay.
Okay.
I thought I was late.
Sorry. No, it crashed on me right when I was in the middle of the sentence, so we'll see what's happening here. All right. So as I was saying, we're going to determine how much energy we need or how hard we have to slap this frozen chicken to cook it. So we're going to assume this thing has a mass of 1 kilogram. And we need a couple more things, and it'll be apparent why we need this in a second. So let's pretend that's a hand. So we can do some guesswork and little Google food. And we can find that the mass of the average human hand is about 0.5 kilogram. So remember, what we're trying to find out is this velocity. So let's think about the physics here. The physics here is that this slapping hand is going to have some amount of energy. Right now, generally, we're talking about a mass that's in motion. So we should be thinking about kinetic energy at this point. The chicken is frozen. And we want to cook it. Well, cooking means imparting heat. Heat is just energy. We measure heat in joules, not temperature. Temperature and heat are two different things. Temperature is a measurement of the amount of kinetic energy in an object. So this is where we use scales, like the Fahrenheit scale or the Celsius scale, the Kelvin scale, to measure temperature. Heat is a measurement of the movement of that energy. So it's a subtle difference. A good way to think about this is, let's say that your body and so it obeys the laws of energy. And it will tend to flow from the high energy state to the low energy state until those two things are equal. This is equilibrium. Well, if you have two things at the same temperature and they touch each other, there's not going to be any heat. Energy in your roughly 98-degree hand. So there's going to be a movement of temperature. So there's going to be heat there. That's why things are going to feel hot or cold. If it's much colder than you, the heat is going to leave you going towards the colder thing, and it's going to feel cold. So that's what you're really feeling.
Dr. J?
Cook temperature, the temperature at which we can say the meat is safely cooked, so I'm not going to die if I eat it. We're going to say that is roughly.
Hey, Dr. J?
Yes.
Can you? Yeah,
Say again?
the freezing up on me. I logged in and.
Is it me that's freezing or you?
You freeze, the whole picture freeze. It's like you log off and you log back.
Wow. Yeah, I don't know what's going on. Is it okay right now?
The Zoom isn't in.
Yeah, you're choppy too.
Because it's.
Let me check something here.
Are you still here?
So I had to turn off all the fans in here so I could hear. Your internet connection is unstable. Yeah, I know.
Yeah, and I have the sound on the high. Really?
Yeah, I don't know. I think it's the internet here. All right. I think we're okay for now. Let's see. What are you doing? Yeah, I know. All right. I think we're okay for now. It may go in and out. So I'm gonna keep doing what I'm doing. And whenever I get done, I will review the video before I post it. And if it's unusable, I will record it again sometime and post it up. So you won't lose anything.
Even when you're talking, it's going on.
Oh, really?
Yeah.
All right. How about now? Can you see me? Can you hear me?
Yeah, I can see you.
Okay, it's not choppy. It's not cutting in and out.
No, it's good now.
Okay. All right, we'll do it again with it. So technology kind of sucks sometimes. That's why I hate doing this online. Anyway, what I was saying is that we need to find the temperature, or we need to find the heat change, the heat energy that has to change in order to get this frozen chicken up to whatever our limit is, 400 degrees, let's say. So the first thing we do from a physics standpoint is we say that the energy from the slab has got to equal the energy required to cook the thing. Now we're making a few assumptions here that are completely unrealistic, but in order to make the math work out and make the problem simple, because I want you to see the process. We're assuming that this energy from the slab is totally conservative, that we are not losing any energy to things like sound. Okay, we're assuming this is a soundless slab. We're going to assume that there's no air resistance, there's no cooling, there's no radiative cooling or convective cooling coming off of this chicken. So we're going to assume 100% efficient energy transfer. So this is going to be kind of our best case scenario for this. Well, we know how to get the energy out of the slab. That's all kinetic, which is a function of the mass of the thing moving and the velocity it's moving at, 1/2 mv squared. We're going to assume that's all the energy in the system. There's not any stored potential or anything. But to find the cooking energy, this is something new that you ever haven't seen. This is an equation for thermal energy. It's the mass times what's called the specific heat times the change in temperature. Remember, heat is really kind of change in temperature. It's not temperature itself. So this specific heat, this is a quantity that tells you how much, basically how much energy is required in order to raise 1 kilogram of something by 1 degree Celsius in temperature. In other words, how many joules of energy do I need to make this 1 kilogram mass increase temperature by 1 degree? That number, that value, is going to be different for every substance. Things with low specific heats are going to tend to heat fast. So most metals, copper, for example, has a very low specific heat. Doesn't require much energy to make copper hot. However, something like asbestos, which is a common fire retardant, needs a lot of energy to make it change temperature. That's why they use it as insulation in old buildings. Never mind that it causes cancer and it's kind of nasty. So the way that we find that energy is we need the mass of the thing, we need how much temperature we need to change it by, and we need whatever its specific heat capacity is. So I know, just for the sake of argument, what I've said is that the mass of this thing is 1 kilogram. I looked up a value, and I mean, this is going to be ballpark again. My value for the specific heat of the frozen chicken is 2720 joules per kilogram Celsius. Very, very strange unit. So this is something sort of like the Newton. Remember, the Newton is a kilogram meter per second squared. And that's really kind of cumbersome to use. So the specific heat is also the same thing. Be careful when you look up specific heat capacities of things that you're using the right units. This is the specific heat in joules per kilogram Celsius. If you're looking for something in Fahrenheit you're gonna have a different specific heat value because it's gonna be joules per kilogram Fahrenheit. If you're using Kelvin, joules per kilogram Kelvin. So make sure that you're using the right specific heat value. So in this case, I'm gonna work in Celsius. So I've chosen a joules per kilogram Celsius. So the last thing I need is my delta T. So remember, in order to find delta, that's final minus initial. So my final is 400, and my initial is 0. So that gives me 400 C. And we can do a quick unit analysis here and see that the kilograms cancel, Celsius cancels, and we end up with something that's in joules, which is what we expect because it's energy, right? So let's pull out the artificial intelligence calculator here and just quickly figure out what this is. So I got something looks like 2720 times 400, and that looks to be about 1.08 times 10 to the 5th joules. So I know how much heat energy we need in joules to cook this chicken. Well, I need to set this equal to the amount of kinetic energy I can generate. So this ends up being 1/2 the mass of my hand is 0.5 kilograms times whatever velocity that is. Remember, we don't know the velocity, but that's okay. That's what we're trying to find. I want to know how hard I have to slap this chicken to cook it in one go. Well, 0.5 divided by 1/2 should give you what? 0.5 divided by 2 should give you 0.25, right? So no, 4.3 times 10 to the 5th meters per second. That's pretty damn fast. Did I crash again? Did it crash again? Come on.
Okay.
Am I back?
Yeah, okay, it happens to you too.
Yeah.
I logged off and logged back on. I thought.
Now the internet keeps going in and out. I don't know what's going on.
Yeah, I'm just gonna watch it for later because if I. It's not
Yeah. Like I said, I'm gonna go, I'll spot check this in a little while and see how it did. And if it really sucks, I'll just re-record it. So
okay. Right. Cool.
what we find is that the velocity required is 4.3 times 10 to the 5th meters per second. That's really damn fast. Well, we can go look at the average velocity. For the average human, just slapping something, your hand is moving at a velocity of about 10 meters per second. So this is on the order of 10 to the 4th times faster than your normal hand slap. There's been a thing going around online that has been, it looks kind of stupid to me. There's these kind of professional slap fighters out there. Yeah, go look this up on YouTube. It's silly. But it's grown people stand across the podium from each other and just try to slap each other as hard as they can and see if they can knock the other guy out. So out of curiosity, I looked up how fast their average slap is. And for those guys, so we're gonna say V-Slap Pro. That's about 25 meters per second. So fast, right? Twice as fast as average. However, we're still not anywhere close to this velocity. If you care, you could find out what the velocity, whoops, you know what? That's wrong because I forgot to square that. Or got to take the square root of that. I thought that was high. It's still going to be stupidly fast. Okay, there we go. It's about 2,080. About 2,080 meters per second. So that's pretty damn fast still, right? Just as a point of reference, the velocity of sound in a vacuum is about 700 meters. Come on. So the ideal problem, we're not losing any energy. That's probably not right. Yeah, no, it's not right because it did wrong. So what are we going to do? What we need to know is how many times we have to slap the chicken with as hard as we can hit it in order to get it cooked. Well, that's basically the same problem, right? Except this time, we are going to start our kinetic energy. We're going to keep our same mass, 0.5. And we know that our velocity, we're going to say, is 25 meters per second squared. Okay. So what we want to know is how much kinetic energy that's how much kinetic energy we get per slap. Well, let's calculate that real quick. So we need a 25 squared, 625 times 0.5 divided by 2. It gives me about 156 joules per slap. Well, if I know it's 156 joules per slap, and I need to generate 1.08 times 10 to the 5th joules of energy, then what I can do is I can say 1.08 times 10 to the 5th divided by 156, because it's how many joules I can do per slap. And let's work out what that is. It's going to be a lot. So 1.08. About 156. That gives us about 69.75 slaps. So we're going to need to just really slap this chicken 6,900 times in a row. Let's play with this even more, just because it's silly. How long does it take me to deliver this one massive 25 meter per second slap? Well, we can kind of estimate this, right? So we're going to assume this is not just a, like a cat popping something off of a counter. I mean, this is really hauling it back, wind up the pitch. So let's say that each slap, so we're going to say one slap, let's just say it's 3 seconds. So we can get one slap every 3 seconds. Well, we know the number of slaps, so look what this is. This is just a unit conversion problem now, right? Except in using things, instead of using things like meters per kilometer, we're doing slaps per second. Fine, that's just a unit. So we use the same skills. So if it takes one slap per 3 seconds, then what I can do, if I need this many slaps, right? Well, if I just divide this by 3, so that's one slap in 3 seconds, right? So actually you can multiply by 3 to make it work. 6,975 times 3. That's 20,925 seconds. Times 24 hours in a day, that's 86,400 seconds. So 86,400 divided by 2925. So that is roughly 4 days. So the answer to our question, can you cook a frozen chicken by simply slapping it, is yes. Physically, it is possible. But as we all kind of know intuitively, that's kind of stupid, and you'd never be able to do it because you could never slap the chicken hard enough. And so somebody has said, well, prove that. Well, that's what we just did. So let's talk about the physics here. Again, we recognize this is just energy conversion. So we need to know how much energy we can make and compare it to how much energy is required in order to change the temperature by a certain value. Well, we know how much energy we can make. That's all kinetic. And we know how much energy we need. That's our heat energy. Set them equal to each other. Solve for the unknown variable. So there's my velocity, right? That's the answer to my question. Yeah, I could do it if I could slap this thing at about Mach 3. Now, as I said, this is an ideal scenario where we are doing 100% energy transfer. In reality, that ain't the case. Because you're going to have things like drag, right? Because you've got the air creates friction. We know friction is a non-conservative force. So it's going to be fact dependent, right? So it depends on how much movement we have. But we're also losing energy as we swing our hand through the air. The air is heating as we do that. Now, not by a whole lot, but this is the same reason that spacecraft need a heat shield when they re-enter, because they're creating friction with the atmosphere. They're generating heat energy. And that's dependent on the velocity. So we're losing energy to heat there. We're creating sound, right? You can imagine if you slap a frozen chicken, it's probably going to make a noise. Probably not going to be black because he's dead. But we're going to make noise. There's going to be a small amount of light energy. Now you're not going to see it, not under ambient conditions. But if you were to look at this experiment with, some photosensor that could pick up individual photons of light, you would certainly generate light energy. And we know that this chicken is going to cool, or the temperature is going to change, right? It's going to be taking in heat from the ambient atmosphere. But if we don't do it in one slap, every time we set up for another slap, we're losing some energy, right? We're radiating out into the air. So if we wanted to do this realistically, it's a very complex problem, but we can see that it would need way, way more energy than just this. It would require way, way more energy than our 1.08 times 10 to the 5th joules. We're probably going to be a couple of orders of magnitude higher than that, which is going to mean that we need an even higher velocity or an even greater number of slaps. We can also assume that we're not all professional slap fighters, so we can double this number effectively. So we're talking about 8 days. So we're talking about you really have to sit there and just slap that chicken for a week, no breaks, 24 hours. You're also going to get tired, right? I mean, there's a lot of people that probably need slapping for about 8 days, and it would be hard to do that, right? I would get tired. So completely unrealistic. Yes, you can do it, but it's dumb and you should never try it. But again, my point with this exercise, even though it's kind of stupid, the point is for you to understand the physics, right? All we're doing is setting up an equality in energy. We have some energy in, and we have some energy out. Because energy is conserved, right? Law of conservation of energy, you can't just create energy out of nothing. You can't just lose energy out of nothing. Those two things have to be equal. If we wanted to account for all those other variables, that's really easy in theory. Because now the energy of the slap is not just kinetic energy. It's the kinetic energy minus the energy lost due to friction, minus the energy lost due to heating of the atmosphere and compression and things like that. Now, those equations themselves get very, very difficult. You get into the realm of differential calculus and variational calculus to have to do that, which is something that you guys are nowhere near prepared for. And that's okay. I just want you to see the thought process. So that means that you have some function for energy on the left, the energy of the slap. In this case, we simplified it and said it only depends on kinetic energy. And we'd have some function of energy on the right, the energy of cooking, which we simplified to just the no loss heat required change temperature of this thing. We assume this was uniform density, uniform heat distribution. It's not. But there are ways you can do that. Again, variational calculus. If you're really interested in that kind of thing, I suggest taking a course called Potential Field Theory that Haidar Al-Shukri teaches in the physics department. Really, really fascinating course and really math heavy, but it really kind of shows you how to do those kind of calculations. So, yes, you can cook a chicken by slapping it if you're really strong or have a whole lot of patience. And I'm a pretty big dude, and I could probably slap chickens pretty hard, but not that hard. Problem is, I don't have a lot of patience to slap the chicken for a week. That's why we invented microwaves and stoves and ovens and things. I'm going to show you one more thing before I move on. I'm going to give you a walkthrough of that last problem on the test that I gave you. I think pretty much everybody understood how to do the first part or the first two parts of it, but that third part gave you a little bit of trouble. I'm not going to work the whole thing, but I want to show you the process that you do. So you remember this problem was here I have a race car and I'm going around some track, okay? And we're going to assume we started at the bottom of the track, doesn't really matter. And what we want to do is, first of all, I asked you to draw a three-body diagram of what's going on here. So certainly we have our weight force, certainly we have a normal force. We're going to have a centrifugal force, and we're going to have our frictional force. So there's our free body diagram, right? Then I asked you to find the velocity. So if we look at this top down, we've got a circle of radius r. Our car is on the outside of the circle going around this way. So I want to find the velocity at which this car is going to slide off the track. In other words, just look at the diagram. I'm not worried about these forces here. The force against the track, the normal force, whatever this ends up being, right? Because those two are going to cancel each other because we don't have any movement in that direction. So what I have to do is effectively say, just like the frozen chicken problem, I want to find the point at which the centrifugal force is equal to the frictional force. Well, we know that centrifugal force is mv squared over r. And we know our frictional force is mu n. Well, we know that our normal force is going to be a function of this angle. So our frictional force is going to be mu cos w, where weight is just mg, but we can leave it alone. So what we end up with, something looks like mu cos theta w equal m v squared over r. Well, I need to know the velocity, right? At which point that happens. In other words, think about the chicken problem. When is the energy on the left side, or the forces? Energy and force are kind of, you can see they're kind of two sides of the same coin, right? So we've got to balance forces. So we want to know frictional force is equal to centrifugal force, so we've set that up. And we want to know this velocity, at which point this happens. Well, there's our V right there. So what do we know? I told you in the problem that you know there's some coefficient of friction, you know, some angle, you know, some weight, right? Because you know a mass, you know, acceleration due to gravity. So there's your mass there. So look at this. If we replace weight with mg, we can cancel the mass, which is interesting, right? And so we can say V is square root, because we got to account for that square, mu cos theta g times radius. So that's our velocity of the car going around the track. Now we got to do something a little trickier. The next part of this thing was I said, okay, let's say at that point, the car slides up the track that has some length L, and it becomes a projectile and lands some distance X away from the track. So I need to know what that distance is. Well, I know what speed the car requires to start sliding up the track. But that doesn't tell me anything, right? That's not necessarily the speed that it's going to leave, because now we got to transition reference frames. I found this speed. What I want to find is the speed right here. We'll call that the velocity of the departure. Well, what's that going to depend on? It's going to depend on the acceleration of the car up the ramp. It depends on how quickly we speed up, right? How do we know that? Remember, from some of the forces, always has to equal MA of the whole system. Well, we know what the sum of those forces should look like, right? We've got our V. So we know that the centrifugal force at this velocity has got to equal to the mass times the acceleration in the system. So what we can do is we can say MA, so that's the whole system, equals M V squared, so it's the square of that, so mu cos theta g r over r. M's are going to cancel, the r's are going to cancel, so we get an acceleration value of mu cos theta g, whatever that is, right? Now what I can do, I know the acceleration. Now I pick a coordinate system that looks like this. This is a linear motion problem now, right? This is from like 3 chapters ago. I know an acceleration and I know a distance. Oh, what's acceleration? Acceleration is velocity per time. Well, I can go to my kinematics equation, right? X equal x naught plus v naught t plus 1/2 at squared. And I know that v equals v naught plus at. I need to find time, right? Or I can use that velocity independent that I can never remember off the top of my head. I always have to look it up. The time independent velocity equation that has the v squared and everything in it. So once we know that, then we know the departure velocity. All right. Now that I know departure velocity, once I know the departure velocity, that's going to be my initial velocity, right? So all I have to do is look at this as a projectile motion problem. This is a cannonball problem at this point, right? Because this theta is still the same. So if we look at our kinematics equation, we're trying to find range. Our x naught is where we started. So we're just going to say our 0 points here. So that's where we started. So our x naught is going to be 0. Our initial velocity is going to be our departure velocity, whatever we found that to be. And we know that that's going to be equal to AT squared, 1/2 AT squared. We need to know the time, right? Just like we did in the cannonball problem. You'd need to go through and find the time. Because you know this thing is going to be some height. So we can assume the height of the track, I guess. And we could calculate that time, plug the number back in, and we finally get our range. It's a little bit longer problem. The reason I gave that to you is because I want you to understand how to start putting all this together. Don't just think about this as memorizing a bunch of equations. I want you to understand what they mean. So for the race car problem, like I said, I expected most of you to get the first two parts, right? Drawing this free body diagrams is pretty easy. If you missed points on that, it was probably because you didn't give me all of this. You probably only gave me a piece of it. But drawing the free body diagram, pretty easy. Finding the velocity at which point the thing starts to slide is relatively easy. But the part where it gets tricky is now you have to go back to what we covered before and recognize that this is just a linear motion problem followed by a projectile motion problem. We did linear motion. Those are very, very easy, right? So we need to find the velocity at the top of the ramp. And then we need to solve for the range equation, which is just some function of that angle. We know how to do that. We did that on the last test and the last couple homeworks. But all we did was solved it one problem at a time. This was actually 3 or 4 problems, which is why I gave it such a high value on the test, because it incorporates pretty much everything that you should have an understanding of in this class up to this point. I could easily, on the final exam, I'm not going to do this, so don't panic. I could, at the final exam, by the time we get there and we know what we need to know about physics 1, I could give you a similar problem to this as the only question on the final exam. Because that would demonstrate to me that you know all of the things you're supposed to know, right? Instead of giving you a traditional multiple choice test. I'm going to show you an example of that real quick. This is the final exam problem. I still remember this. This was 30 something years ago. When I did my undergrad in physics, I was at Auburn University at the time. This was the final exam problem in my physics 1 class. Yes, I said the problem. It was the only one. Here's a bowling ball with some mass big M and some radius R. We have a block of wood of some mass small m. We apply some force to the bowling ball at some angle theta. which is going to cause the bowling ball to start moving with some velocity of rotation. There's some friction between the block and the bowling ball. And so the question was, find the length of the arc made by the block before it falls off the bowling ball. At some point, this is going to slide enough that it's going to depart the bowling ball, right? Friction's no longer going to be able to hold it. So this was the question on the final exam. Look at all the cool stuff that's in here. This is some of the forces. This is rotational motion. This is linear motion. This is figuring out how to do this arc length. There's frictional stuff in here. I could even make this a little more complicated and say, what if I have some other mass? Let's say this is a billiard ball, and I throw the billiard ball with some force and hit the bowling ball and make it start moving. Now I've got a collision. So this is the point where you go, but we haven't learned collisions yet. You're right, you haven't. Guess what I'm going to start talking about next time? We're going to talk about collisions, talk about things hitting each other. We're going to talk about why billiards works and wonder why I suck at it so bad when I can explain the physics, but I cannot apply it in practicality. So that's where we're going with this class. Is we're going to start doing collisions next time. If you have questions, problems, concerns, as always, send me an email or stop by my office and we will handle it. Other than that, I will see you guys at the next lecture.